Thanks for the introduction. So this talk is about multirotors, which are redundant. Redundancy means that you have more than one way to execute the same branch. So I'm here focused on the branch task. So what is typically devoted to control allocation. Redundancy and underactuation are not in opposition. Sometimes this is confused. So there are platforms which are non-redundant, like the quadrotor or the fully actuated Hexarotor. And but the first is underactuated and the second is fully actuated. While there are platforms that are redundant, like underactuated Hexarotor and the fully actuated Octorotor. So I am interested in the second column in this scheme. Redundancy creates fibers. What are fibers? On the left of this plot, we see the original space of the velocity of the propeller. And on the right, we see the task, the branch. In a simplistic case of a two-dimensional branch and three-dimensional number of propellers. So you see that to each point on the right corresponds a manifold, which is a fiber, a one-dimensional manifold in this case. And every point, if we put the velocity of the propellers in every point on this line, on this curve, we get the same exact task. So the problem is not for redundant actuators whether we can do the task, but where we should do it. Typically, in the literature, we use one criterion, which is energy. Standard allocators, for example, when you use the pseudo-inverse map, they minimize typically the energy or the control effort, okay? But this it's only one side of the coin, because responsiveness to changes or the ability to change the task, the branch very quickly, depends also on where on the fiber we put our velocities. So as you can see here, we have two tennis players. This is minimum energy, okay? But if you want to be responsive, you still. So the total branch is the same, but it's very different, the posture. So you are on the same fiber, but the responsiveness is very different. And in fact, I did a biological example in this case with a human, but this is well known in the animal world. So there are muscles which use this idea to trade off energy with promptness. If I want to be very prompt to catch a ball, I tense my muscle so that I can move my hand very quickly. While if I want to save energy, I relax my muscle. I'm applying the same task, so the total torque is still zero, but or just compensating gravity, but it's the same value. But I am much slower in moving because my muscles are less tense. So now bear with me, a couple of slides in which I put a bit of math. You don't need to fully understand it, but the idea is that when you have, why promptness is interesting and where it generates from? It generates from the limits in the motor torque. If there were no limits, then it doesn't really matter where you are on the fiber because you have an unlimited amount of torque. You can have an unlimited speed in the acceleration in the motors, and then you can go everywhere in a very short amount of time. When you have limits, then this is where this metric matters. And actually, I use the word metric, but because the limits can be associated to a metric. And then the idea, in order to see this promptness in the space on the right, the task, you have to push forward, in differential geometry terms, is called the metric of the velocities of the propeller space, okay? So this is done by taking the Jacobian or the differential of the nonlinear map and taking the metric and pushing it forward. From a graphical point of view, this is the landscape. You are on the tangent space, where the acceleration of the propellers are on top right. Maybe you can see my pointer here. You want to go on the tangent space of the task's rates, and there is the differential which maps the two, but you have to push forward this metric. This is the metric in the velocity propeller space, and you push it here so that you have a metric that tells you how quickly you can change the task at a certain working point. In fact, the working point V here is where you do the tangent space. So this is for the lovers of a differential geometry. So, but in the end, what is practically this promptness, this ability to change the task quickly? You can imagine it as the density of the fibers. If the fibers are very dense at a certain point, it means you can change the task by moving by a small amount the velocity, by changing by a small amount the velocity. If the fibers are very not dense at all, then you have much less promptness. But the density, it's first of all, it's something that is it comes from two concepts: the geometric concept of the fiber and the orthogonality to the fibers, which is defined by the metric. The two things have to be together, and this is why you have the determinant of D, this matrix, which encodes both the nonlinear map, the fiber, which defines the fiber, the Jacobian here, and the metric. So it's really the merging of these two concepts, the metric and the geometry. And this is a geometric field. You have this density, it's a geometric field. The higher rho, this density, the better the promptness. Here you see the fibers as before, and on the bottom you see low density, high density region, and on the top you see a low density region. Okay, and this surface that you see are possible allocators. You can select a point in this surface to have the task you want. If you select on the first surface on the top, you have low density fibers, low promptness. If you select on the surface on the bottom, you have high density, high promptness. So let's specify this theory to the case of the quadrotor. The map of the quadrotor is the standard nonlinear map with sine quadratic map here. So this is the nonlinear map. So now what we have to do is to compute the density on it with the previous formula. And at the same time, we can also compute the power consumption on it. The power consumption, it's related to the cube of the absolute value of the speed. This is just the standard power consumed to fight the rotor drag. And instead and it gives the first cost function. The second cost function instead is given by this promptness. But in order to be a cost function, you have to put a minus in front of it, and you can also square it to remove the square. Okay. And actually here we have to use a metric, to choose a metric, and we can choose, for example, the Euclidean metric. Okay, this is the formula with the Euclidean metric, but the formula works also for any other metric. Now, when you plot this, okay, now this holds for n-dimensional, so n number of rotors. But to stick to fix the ideas, let's look at a very prototypical example, which is also redundant: a cart with two propellers that can move only in one direction. So the task, the force that is produced to move this cart is one-dimensional. The propellers are two, so you have an infinite number of ways to generate the same task. You can imagine these propellers even pointing both up, and you have a birotor is exactly the same. So when you write down the two costs for this particular case, you have these two fields. So the bluer, the better, okay? It's smaller. You see that the promptness and the power, they are exactly the opposite. If you want more promptness, you have to increase somehow the norm of the propeller speed. If you want less power, you have to decrease it. And now, but now there is another important role, which is which type of speed you select, depending on how you orient the propeller, or whether the propeller are monodirectional or bidirectional. And so, for example, if the propellers are both pointing in the same direction, so they produce a thrust that is pointing in the same direction, both, so they can only generate positive thrust, they cannot, in the case they cannot reverse. When you put the sign in the previous formula, you get this formula. So and this is the formula of an ellipsis. So you see on the right here, ellipsis. So, and each ellipse is a particular fiber, a particular task. Now, if we instead put them in opposition, so one thrust in one direction, another thrust in another direction, they are antagonistic in co-contraction, then the fibers look topologically very different. They look hyperbolas because there is a minus here. and they are indefinite. They are not anymore a compact set. In the previous case, you had a compact set. So the fiber topology decides whether, as we will see now, the tuning of the promptness is possible or not. You can already imagine that if you are here, you can tune the promptness because you can increase the norm by staying on the same fiber. While if you are on the green region, you cannot increase much the norm of the fiber of the velocity. So you cannot really modulate much the promptness. And here we see this. So in cooperation, the fibers, they go more or less along the level curves of the two fields. The Pareto front is very small, but so there is no much opposition between the two actually costs, but also you cannot tune much the promptness in this configuration, so in cooperative configuration. Instead, in antagonistic configuration, the fibers look like hyperbolas. You can move along the hyperbola and indefinitely increase, in theory, the promptness, but at the cost of an increased energy. So the Pareto front is very large. You have a lot of tuning capability. And this is not only for a birotor. This is the case, for example, of an hexarotor that I showed before. And you see that increasing with a low promptness, the value of the velocity is up to 200, for example, here, hertz, but the derivative is very high. While the larger the promptness, you get a larger absolute value of the velocity, almost 320, but the derivative is very small. So small variation make a large variation of the task, but you need to go to higher energy regions. And this is the exact same map appears on muscles and variable stiffness actuators, which are the robotic counterpart of muscles. You have two motors with two tendons that can control one link. Okay, if you look at the map in this literature that you find in this literature for the torque produced by this link, you see that it depends on the elongation of the two tendons. And if you compute this for a specific theta, for example, 0, and you assume that, for example, the tendons are quadratic hardening type of tendons, then you get exactly the same formula that we had before of the two rotors in opposition. But now, what is the isomorphism? So that the length of the tendons corresponds to the velocity of the propeller. Okay, so these are the two variables that match with each other. The fibers look the same, but the spaces are physically different. They are velocity of the propellers or length of the tendons. But you can conclude the same exact mathematical conclusions. So I'm concluding now. The fact is that these variable stiffness actuators are named after the stiffness. Why? Because the stiffness is the derivative of the force with respect to the external the angle. So there is the perceived stiffness by an external actor, let's say. However, as I prove in the work, an increase of the stiffness causes also a monotonical increase of the promptness. So stiffness and promptness, they are kind of the same thing, but even if mathematically the numbers are different, the function are different, but they are monotonically related. So we can say that variable stiffness actuators and multirotors, when considered in the sense of maximizing the promptness, they behave in the same way. And in fact, actually, we could call also variable stiffness actuators as variable promptness actuators. Nobody ever did it because they didn't look at this thing, but at the best of my knowledge. So in conclusion, aerodynamic promptness is the fiber density induced by the aerodynamic map. Here you see the field. So there is a field induced by the aerodynamic map and a metric, actually. On the velocity field. Here is in 2 dimensions, but it holds the formula in n dimensions. The energy promptness is fiber and metric dependent, and it's in the part in which the rotors cooperate, you have a weak tuning capability of the promptness. In the part in which the the rotors instead are antagonistic, the forces are antagonistic, you have a high capability of tuning. And so basically we can see through this lens how a multirotor behaves in flying and in implementing the desired branch as a muscle group. Okay, so this was an interesting analogy that I found. I think there are also several other extensions possible, and also with this analogy, and also to study the Pareto fronts in the multidimensional case, and also to test different type of metrics and to see which one could be the best beyond, for example, the Euclidean one. Thank you for your attention. If you are interested, you can also read these other preprints which give a corollary to these results. Thanks a lot.